Once again, you're welcome to waidusmacademy. Today we'll be looking at chemistry chapter 1, the states of matter. We'll be looking at state of matter. Okay, without wasting time, let's first of all quickly listen to our tutorial, and then after that,
In this video, we will be looking at solids, liquids and gases. Materials come in three different forms: solids, liquids and gases, also known as the three states of matter. You must be able to describe the particle arrangement for each state and link this to its properties. So let's start with solids. Solids have their particles close together in a regular arrangement. There are strong forces of attraction between the particles, so they don't move but vibrate around fixed positions. The particles in a liquid, although close together, are able to slide past each other, as the forces of attraction between the particles are weaker. The particles in a gas have very weak forces of attraction between them, so the particles can move randomly and quickly in all directions. As we can see, the energy of the particles increases going from a solid to a liquid to a gas. The opposite is true for density, which will decrease going from a solid to a liquid to a gas. Make sure you can apply this arrangement to any given substance in an exam. Let's have a closer look at the properties for each state. The particles in a solid are unable to move and have no spaces between them. So a solid is rigid and maintains a fixed shape and a fixed volume. Because of this, a solid cannot be compressed when pressure is applied. Solids also have a high density. The particles in a liquid are also close together, so like a solid, a liquid is hard to compress. Because the particles in a liquid are able to move over each other, liquids do not have a fixed shape, so they can flow and take the shape of their container. They do, however, have a fixed volume. Some students find them having a fixed volume but not a fixed shape confusing. So imagine you have 1 litre of water. You cannot change the volume of the water to suddenly become 2 litres, but you can pour the water to fit the shape of different containers. Liquids have also got a lower density than solids. The particles in a gas move quickly and randomly in all directions. A gas therefore has no fixed shape or volume and will completely fill a container. Due to the particles in a gas being far apart with large spaces between them, a gas can easily be compressed. The particles will also collide with each other as well as with the surface of the container they are in, which creates pressure. They have a much lower density than solids and liquids. This question asks you about the separation, arrangement and motion of particles in element X, which you are told is in the solid state. The question is 3 marks, so you will score 1 mark for a statement addressing each of the terms in the question. To help you answer, think about the structure of a solid we looked at earlier. Looking at this model, we can see that the particles are close together, which answers the separation element of the question for 1 mark. The particles have a regular arrangement, which will score your 2nd mark, and they are unable to move properly. They just vibrate around fixed positions, which scores your 3rd mark. Make sure for any question on states of matter that you refer to particles within your answer, instead of generic terms like they. This question is extremely similar to the one we've just looked at, but is asking you to describe the arrangement and separation of the molecules in hydrogen chloride gas. This question is 2 marks, so again, it will be 1 mark for describing the separation of the particles and another for describing the arrangement. The structure of a gas is shown here. As we can see, the particles are far apart from each other, which addresses the separation element of this question for 1 mark, and they are arranged randomly, which scores the 2nd mark. You would also score the 2nd mark for saying that the particles are not in fixed positions or they are not in fixed arrangement. To summarise, there are 3 states of matter: solids, liquids and gases. The particles in a solid vibrate around fixed positions, meaning that solids have a fixed shape and a fixed volume. The particles in a liquid are able to move over each other, which means that liquids have a fixed volume but not a fixed shape. The particles in a gas are far apart and move quickly in all directions, meaning that gases have no fixed shape or volume. Make sure you can describe the arrangement, movement, separation and energy of the particles and relate this to a substance's properties. Don't forget to check out all our other fantastic revision resources here at Save My Exam.
Okay, so we've quickly listened to the tutorial, and then we know what solids are, liquids are, gases are, so we're not going to bore you with a lot of that. But just remember, solids, the particles are very close together, so they're in a fixed shape, and the particle can only move by vibration. They only vibrate about their fixed position. So solid particle only vibrate about fixed position. That's it. they have fixed shape and fixed volume. They have fixed volume and fixed shape, and they have high density. The atoms only vibrate about their fixed position. Okay, so we can say the particles are packed close together in a very regular pattern. Now for liquid, we say the liquids, they have what we call the fixed volume, but they don't have a fixed shape. Because if you put 2 centimeter cube of water in a container, you can change the container, the shape of the container, but the volume remains the same. Okay, so liquid, the particle can only move slightly over each other. Okay, they're not in a fixed shape, they can slide over each other. Okay, and then we say the liquid also very difficult to compress, even though the density is lesser than that of solids, is relatively high. The force of attraction between them is relatively weaker than that of solid. Now, in case of gas, the gas do not have a fixed shape, neither does it have a fixed volume. The particles are spread out, they're far apart, and they are able to move very randomly. So in terms of arrangement, they are far apart, and in terms of their movement, they move randomly. The particles move very randomly. Okay, so that's for gas. And then we say because of gas can be compressed because particles are super far apart. So they can be compressed. When you compress it, you increase the rate of collisions of particles, therefore pressure will increase. When you reduce the volume, pressure increases. When you make the volume bigger, pressure reduces in the case of gas. Okay, now let's take a look at them diagrammatically from what you see. That you can see the arrangement. This is solid, the arrangement of particles of solid. They're in a regular pattern. You see the particles are arranged in a regular pattern. Okay, they have a regular arrangement, regular pattern, and they don't move. The particles don't. They only vibrate about their fixed position. So in terms of movement, they vibrate about their fixed position. That's what you explain in terms of their movement. Now, in terms of closeness of particles, you say they are very relatively close. The particles are close, and in terms of density, they have high density. Solid have high density, of course, because their particles are very close together. Now, energy of the particle is low here. The energy is not very high, so they cannot move. So it has a low energy of particle. So in terms of liquid, the particles are close, but not so fixed in a position. They're able to slide past over each other. So we can say in terms of arrangement that the particles are arranged, randomly arranged, and they move around each other. They slide over each other. Then in terms of, we can say they are close. Not very close, but they are close. The particles are close in terms of closeness of particle. Then in terms of density, they have a medium density, not so high, not so low. Then in terms of the energy of the particle is greater. That's why they're able to move. Unlike this one has a very weak energy, okay, or low energy. Energy here is greater than that of solid. So the energy, I'm talking about the energy of the particle. So the particles are able to slightly move. Then in terms of gases, they're randomly arranged. Particles are super randomly arranged, and they move quickly in all directions. They can move in all directions, collide with themselves, and collide with the walls of the container. And then we said in terms of closeness of particles, you can see the particles are not close; they're far apart. In terms of density, they have low density because particles are way far apart. And in terms of energy of the particle, we say that they have the highest energy. That's why they can move very tremendously. Okay, that's why they can move very tremendously. Okay, let's move to the second part of today's class, which borders on still on the state of matter. We'll look at the change of state, how we can change a substance from solid to liquid to gas, or from solid to gas without passing through the liquid state, which is called sublimation. So we're going to look at each of these. So, but before we do that, let's do the tutorial. Let's take a look at the tutorial. Okay, let's take a look at the tutorial first before we explain this concept.
In this video, we are going to look at changes of state. As we already know, the 3 states of matter are solids, liquids, and gases. Substances can change from one state to another, and you must be able to identify the change of state which has occurred. Let's start with a solid. Heating a solid up will transfer energy to the substance, causing it to melt and form a liquid. If further energy is transferred, it will evaporate and then form a gas. Some diagrams will show a liquid to a gas as boiling. Although you can give boiling or evaporation as an answer if you are asked for this change of state, it is important to know the difference. During evaporation, only the particles at the surface turn into a gas, and it does not occur at a fixed temperature. Boiling occurs when all of the molecules throughout the liquid turn into a gas, and does occur at a fixed temperature, the boiling point. As energy is transferred from the gas back to the surroundings, the gas will condense to form a liquid, and then freeze to reform the solid. Sometimes a solid can change directly from a solid to a gas, or from a gas to a solid, without becoming a liquid in between. Changing directly from a solid to a gas is known as sublimation, and a gas to a solid is called desublimation, also known as deposition, but you will not be tested on these two in your exam. Common exam questions expect you to be able to name the changes of state occurring for a given substance. Part A of the question shows the physical changes that element Y can undergo, and you are asked to name each one. Although this is a straightforward question, pay attention to the numbering. Students often identify the correct changes of state but write them in the incorrect order. Here we can see that physical change 1 is going from a solid to a liquid, so should be melting for 1 mark. Physical change 2 is from a gas to a liquid, so is condensing. Physical change 3 is from a liquid to a gas, so is evaporation. However, as discussed, you could also say boiling. Change 4 is from a liquid to a solid, so is freezing. Part B gives you one difference between boiling and evaporation as the rate at which the processes occur, and asks you to state one other difference. Remember, we said that evaporation only happens to particles on the surface of the liquid, whereas boiling happens throughout the liquid. Either of these answers would score 1 mark. You could also say that boiling happens at a specific temperature, or that evaporation happens over a range of temperatures. In summary, a change of state occurs when a solid, liquid or gas turns into another one of these states. You must know the following changes of state, including melting, freezing, boiling and evaporation, and condensing. Remember, evaporation and boiling are different because evaporation involves only the surface particles of the liquid changing into a gas, whereas boiling is the process of the whole liquid changing into a gas. Don't forget to check out all our other fantastic revision resources here at Save My Exams.
Okay, now let's continue. We've heard the change of state, how we can change from solid to liquid, liquid to gas, or we change directly from solid to gas, or directly from gas to solid. Okay, so let's quickly take a look at these changes and the term that are used with it. Say, state changes occur when solid becomes liquid. That's when a solid melts. When you heat a solid like ice, let's take an ice block from the refrigerator. When you heat it, it will melt. So the process of changing it to liquid, changing an ice to liquid is melting. Okay? Then when you keep heating the liquid, it will start to boil or evaporate. So boiling or evaporation will change it to gas. Now if it's already gas and you remove it from heating, you start to cool it. It will cool to a certain level, it becomes back to liquid. That's condensation. And cooling a liquid further by putting it in the refrigerator means freezing. And then you get solid back. Now, but there are some substances that can sublime. That can, when you heat them, instead of changing to liquid, they will, like iodine, they will change straight to a gas. That process is called sublimation. A good example is iodine, and another example is carbon dioxide. When you heat them, they change straight to a gas without passing through the liquid state. They will not melt to become liquid to gas. They just from solid straight away to becoming a gas. And also there's what we call desublimation. Something that is a gas can be cooled to become solid. Same examples that I've just given. Okay, so this is very important in your exam, this diagram, even though it looks very basic, but you need to remember it very intensely. So we already know what melting is. Melting is when a solid changes to a liquid. Okay, you must remember this at 0 degrees Celsius. It requires heat energy which transforms into kinetic energy. Okay, the heat energy from whatever you're using to heat it will transform the heat energy to kinetic energy of the particle. The particle will gain kinetic energy in order to break loose from their liquid, in order to break loose from their solid state to become liquid. Okay, so, and we also say melting occur at a specific temperature known as the melting point. The melting point is the temperature at which the solid turns into a liquid and which has the same value as the freezing point also. So, and it's usually 0 degrees. Is that okay? Now the second one is the freezy. Freezy is when we take a liquid and put it in the refrigerator in a cold place, allow it to turn to solid. So freezy is when you change a liquid to a solid. And this also has same temperature, which is 0 degrees Celsius. So the temperature of freezy is also 0, and temperature of melting a solid to a liquid is also 0 degree. So both freezy from liquid to solid and solid to liquid, they're both 0 degree Celsius. Now we say for boiling, let's take a look at boiling, the case of boiling. Remember in freezy, same temperature, everything happens at same temperature, freezy and melting. Now for boiling, boiling is when a liquid changes to a gas. When you put like water in your Bunsen burner, you heat it, and a time will reach, especially when it reaches 100 degrees Celsius. When it reaches 100 degrees Celsius, you begin to experience that the water particles bubbles start to be formed. So boiling is when a liquid changes to a gas, and it requires heat, which can cause the bubble to become a gas, okay, to form a gas. And it's usually 100 degrees Celsius. And this temperature is known as the boiling point of a liquid or water. Evaporation, on the other hand, is similar to boiling, but slightly different from boiling. Evaporation, what happens is that the liquid is left, you're not heating it on the Bunsen burner, the liquid is left outside in the sun, so the particle on top of the surface of the liquid gain more kinetic energy and are able to escape into the atmosphere. So in in evaporation, only the top surface of the particle gain higher kinetic energy and are able to escape into the atmosphere. So it does not happen, evaporation does not happen throughout the surface of the liquid, it happens only on the top surface. Condensation is when we decide to change a gas back to a liquid. So you allow the gas to cool, okay, like steam. Steam is a gas, a form of water vapor. Water vapor is a gas. So when you allow it to cool, over a range of temperature, then it becomes a liquid. So condensation is also a process that is very, very paramount. Now, before we go to kinetic theory, the basic kinetic theory, let's take a look at this further tutorial before we can expatiate on the kinetic theory.
In this video, we are going to look at changing states in kinetic theory. As discussed in the previous video, changes of state take place between solids, liquids, and gases. Kinetic theory looks at the behaviour of particles to explain why this happens, so let's start by looking at a solid. When a solid is heated up, the particles absorb energy, causing them to vibrate. Eventually, they vibrate so much that the solid expands and the bonds between the particles break, causing a liquid to form. If the liquid is heated further, the liquid will continue to expand, the remaining intermolecular forces will be broken, and the particles will gain enough energy to evaporate and turn into a gas. At the boiling point, the whole substance will change state from a liquid to a gas. Now let's take a look at what happens in the opposite direction. When energy is transferred from a gas to the surroundings, the particles lose energy and begin to slow down. The distance between the particles decreases, some of the intermolecular forces will reform, resulting in the formation of a liquid. If further energy is transferred, then bonds will reform between the particles and a solid reforms. It's important that you are able to explain in terms of energy why these state changes occur. Heating curves show how the temperature of a substance changes as it is heated from a solid. From this we can see where the changes of state occur. At the beginning, the temperature of a solid increases as it is heated up until it reaches its melting point. At its melting point, the line becomes horizontal, indicating the temperature does not increase during melting. This is because the energy is used to break the forces holding the particles together and turn the substance into a liquid. Once the melting process is finished, the energy transferred continues to increase the temperature of the liquid, which again we can see from this slope here. The temperature will continue to increase as heat is added until the boiling point is reached, which again is represented using a horizontal line. This is because the energy is used to break the remaining forces between the particles so that they can escape from the liquid. As a result, a gas will form, which is shown increasing in temperature at the end of the graph. It is important that you are able to interpret these curves and identify what change of state is happening at different points. Remember, during a change of state, there is no change in temperature. A cooling curve just shows the opposite and shows the changes of state which occur when a gas is cooled down. The slope lines show how the temperature of the solid, liquid, and gas decrease, and the horizontal lines represent the changes of state, condensing and freezing. A cooling curve is just a mirror image of a heating curve. This question tells us that a gaseous substance is slowly cooled. Before you answer the question, it can be useful to interpret the cooling curve. Remember, the changes of state are shown by horizontal lines, and the sloped lines show where the gas, solid or liquid is being cooled. The question tells us that we start with a gaseous substance, so A must be a gas. As the gas is cooled down, it will turn into a liquid, which we know is condensing, and is represented by the letter B. The liquid continues to decrease in temperature, shown by C, until it reaches the freezing point at D and becomes a solid. Part A of the question asks for the change of state that occurs in region B, which we can see for 1 mark is condensing. Part B of the question asks at which point the substance will become a solid. This will be at the freezing point, which is at D, and again will score you 1 mark. This next question focuses on nitrogen dioxide. The question explains that when it is cooled, it forms a yellow liquid and then pale yellow crystals. The crystals are heated and the temperature measured every minute. Part A asks you to describe the arrangement and movement of the molecules in region A to B. So as we did before, let's start by interpreting the graph. Section A of the graph will represent the solid, as nitrogen dioxide crystals, as the question explains, are being heated. For part A of the question, you therefore need to describe the arrangement and movement of particles in the solid. From an earlier video, you should know that particles in the solid are arranged like this. The particles are closely packed together and arranged in a lattice, with the particles vibrating around fixed positions. This answer will score you 3 marks. Looking at the graph, the temperature of the solid will continue to increase until it reaches its melting point, which occurs in the region of B and C. You would also score the mark for freezing, as this is the change of state that occurs in the opposite direction. Once the substance is melted, the liquid will continue to increase in temperature, which is shown between C and D. In summary, kinetic theory explains why solids, liquids and gases change state by looking at the behaviour of the particles. You must be able to explain why a substance changes state by referring to the energy of the particles and the forces between them. You must also be able to label and interpret cooling and heating curves, which are used to show how the temperature of a substance changes as it is cooled down or heated up respectively. Don't forget to check out all our other fantastic revision resources here at Save My Exam.
Okay, so we've taken a look at this tutorial on the kinetic theory, okay, of matter, or kinetic theory of matter. Now we say the state changes and the kinetic theory. We've already understood the solid, liquid, gases, the particle arrangement, the separation, the vibration, the movement, all of this. We've taken a look at all of these things, right? Now we say when substances are heated, the particle, they will absorb the energy. They will gain thermal energy, and which is then converted to kinetic energy that will enable the particle to be able to move further. Now this is the basis, or the true foundation of the kinetic theory of matter. This is the foundation of kinetic theory of matter. When substances are heated, they absorb thermal energy, and this thermal energy are further converted to kinetic energy to enable the particle to move. To break the thermal energy breaks the bond that holds the solid particle together, and then give them that kinetic energy to be able to move, and changes to liquid and they'll be able to move. Now heated solid causes the particles to vibrate more. If you heat a solid and to vibrate to a point that it will start to expand. When it expands, it becomes liquid, and when you continue to heat it, it will expand to a level of becoming a gas. Now, this is when the solid melts and changes to liquid in the first instance, and further heating, the liquid will evaporate and become a gas. Okay, so this gives rise to what we call the heating curve. We have the heating curve and the cooling curve. So at this point, you have a negative value here, not 0. The 0 is at this point. The 0 is at this fixed horizontal point. 0 degree is here. Here is negative anything, whatever. So this between negative something to 0 is solid. It's solid. Particles, you can see that in a fixed position. They are arranged in a fixed position and in a fixed manner. So at this point, you have a mixture of solid and liquid, because melting is taking place in this point. Some particles are still in their solid state, and while some have already changed to liquid. But at this beginning point here, everything has changed to liquid. So going forward from here is now a liquid. Going forward from here, it means the particle has changed state completely, or the state of that matter has changed completely to a liquid. Okay, so at this point is the beginning of gas. So at this point now you now have liquid gas in a mixture. This is called vaporization or evaporation or boiling. So at this point, the beginning here, we start to have gas completely, and everything onward from here becomes a gas. This plot of temperature against time is called the heating curve. It's called the heating curve. Similarly, we have what we call the cooling curve. In as much as we have a heating curve in the first phase, during heating, during cooling and freezing, we also have what we call the cooling curve. A plot of temperature against time also reveals that when you cool the gases, a point will reach where they will start to condense. Okay, as you cool the gases, a point will reach, they start to condense. During that condensation stage, the particles are a mixture of gas and liquid. Then it will reach a point here where everything becomes liquid down this slope. So along the slope here, everything becomes liquid, and at this beginning point, you have a mixture of liquid and solid. So this point is called freezing because you put the particle in a refrigerator, you cool it, super cooling it. So a point will reach when it becomes solid, okay, when it becomes solid. So this is called the cooling curve, while this first one is called the heating curve. This is where IGCSE brings their questions, the cooling curve and the heating curve. This is where they normally bring their question. Now let's go to the next one. Now we're going to look at the pressure and temperature in gases, okay? So here we talked about heating the particles, heating the substance, the matter, state of matter. When you heat it, they get thermal energy. The thermal energy is converted to kinetic energy, which enables the particles to expand. As it does that, there's a frequent collision now there's more collision between the particles and between the walls of the container that you're heating. So the particles start to collide with themselves and increases their speed. The velocity of the particle become increased. As you increase temperature, the velocity of the particle increase, which is called speed. Speed and velocity, in this regard, we are using them interchangeably. So you've increased the speed of the particle of the gas, and as you increase speed, kinetic energy will increase. As kinetic energy increases, the particle will be able to evaporate more and further. The gas will increase. The pressure of the gas will increase. So as we increase temperature first leads to increase in the speed of the particle, which result to more frequent collision between the particles and the walls of the material, which automatically increase the momentum, because when momentum is mass times speed velocity. So when the speed is increased, the momentum of the particle also increase. So as that happens, then the pressure increase, the pressure of the gas increase. Is that okay? So these are what the kinetic theory of matter elucidates or explains or gives to us. As temperature increases, the gas volume increases. The gas will definitely increase, and the density decrease. Density will decrease. It will not be more dense because the particle will be further apart. So the density will decreases, and the volume increases. So the balloon rises. So the volume increases, then the balloon can rise. Okay. So when you want a hot air balloon, that's why we call it the hot air balloon. Why we put a little bit of fire in a hot air balloon is to cause the speed of the particle to increase. As they increase, the density will reduce, and as density reduces, the volume will increase, and the volume of the particle increase, the pressure will increase, and then the balloon will rise. Okay. Gases are kinetic theory. Like we said, the gaseous particles are in constant random motion. These particles, they move in every direction. They are in constant random motion. They hit themselves, and they hit the walls of the container. See, this one hit this wall, and it's bouncing, it's changing direction to this way. So they are moving randomly, zigzagly. Okay, zigzag. They are moving zigzag in a zigzag manner. This one hit the wall at this point, and then it's going this direction, bounce off. So they hit it themselves and hit the walls of the container. So gaseous particles are in the constant random motion. They're always moving. And the pressure that a gas creates inside the closed container is produced by the gaseous particle hitting themselves inside the container and hitting the walls of the container as well. And when you force over an area, when you hit, this is moving with a force. So when you heat an area, force over area is called pressure. Force over area. Pressure is defined as force per unit area. Force over area is pressure, which means as more frequently they heat themselves and heat the walls of the container, the greater the pressure, because the more force over area that is there, that is produced. More force over area that is produced. And then the greater the pressure. Okay? The pressure of this thing in the container. How does the temperature affect the volume of the gas? Now, increases the temperature, increases the kinetic energy of the particle, right? Kinetic energy will increase. When kinetic energy of the particle increase, then the thermal energy from the increasing temperature is converted to kinetic energy in the particle, right? The thermal energy. How do kinetic energy increase? Because the thermal energy from the heat is converted to kinetic energy. Now, as the temperature increases, the particle in the gas move very fast and they spread out. They move faster. Speed increase. Temperature increase, speed decrease. Temperature increase, speed decrease. When speed decrease, kinetic energy will increase, because if you look at this equation, kinetic energy equation, if you look at kinetic energy equation, Ke is half mv squared. Ke is half mv squared. So how then do we say half mv squared? M is the mass. This is the formula for kinetic energy. And this V is the speed or velocity. So when temperature increases and you say the speed of the particle increase, they move very faster randomly. So if speed increases, you can see the speed is directly proportional to kinetic energy. Kinetic energy is directly proportional to speed. And so in that light, if the speed increases, kinetic energy will increase. And if kinetic energy increases, it means that there's more frequent collision between the particle. There will be more frequent collision between the particle. And when there's more frequent collision between the particle, momentum increase, and then the pressure of the gas container increase. The pressure of the gas container will increase. Now, if the gas particles are inside the container, they will collide more frequently with themselves and with the walls of the container. They will collide frequently with themselves and with the walls of the container. Now, if the container walls are flexible and stretchy, then the container will be bigger and bigger, just like the hot air balloon we've taken a look at earlier on. So that's how the temperature increases volume. So if it's a light material, as the temperature increases, the speed of particle increases, particle hitting the walls, and so the wall will be getting bigger and bigger, just like the hot air balloon. Now let's take a look. How does the pressure affect the volume of the gas? Actually, this one, when the volume is bigger, pressure is reduced. Pressure is reduced. Why? When volume is big, it means it takes a bit of longer time for the particle to hit each other because they are more spread out. It takes a bit of longer time. It's a common sense. When this volume is big, these particles don't have a very short space. They have space, a little bit more. So they collide a bit later than this one. When the volume is halved or reduced, you can see that the particles are very close, so they can easily hit themselves. And the more particles hit themselves and hit the walls of the container, the higher the pressure. The higher the pressure. Because the more collision, the more the pressure. The more force over area, because pressure is simply force over area. Pressure is what? Simply force over area. Pressure of the gas is simply force over area. What is force? It means force is particle hitting the walls of the container. The rate at which the particle collide, rate of collision of particle. So the more particle collide with the walls of the container, with themselves and with the wall of the container, the greater the pressure. So if you reduce the volume, technically if we reduce volume to this level, let's say we have and we spread the particles out here. If we reduce the volume, then there will be more frequent collision. If we reduce the volume, there will be more frequent collision. And if there is more frequent collision, pressure will increase. Pressure will increase. The more frequent collision we have of the particle colliding with themselves and with the walls of the container, the greater the pressure. Okay, unlike if you make the volume bigger, okay, the particles are well spread out. So the time of impulse or the time of collision is higher. They don't collide more frequently. The particles don't collide frequently because they are well spread out. It takes a little bit longer time to collide with themselves. So pressure is reduced here. Pressure is reduced here because Pressure is the rate of collision of particles, the rate at which particles collide quickly with themselves and with the walls of the container. That's the measure of pressure. Is that okay? So when you have volume, which means technically pressure and volume are inversely proportional. Technically, we can say pressure is inversely proportional to volume. Pressure is inversely proportional to volume. Meaning, if you make volume smaller, pressure will be bigger. If you make volume bigger, pressure will be smaller. If you make volume bigger, pressure will be smaller. Just like you have here. You make volume smaller, pressure will be bigger here when the volume is reduced. Or like here, pressure will be smaller when volume is bigger. The more frequent collision of gas molecule with the container wall, the higher the pressure. The gas molecule collide with the container wall. Here, they are just showing you what is happening. So from this way to this way is increase in pressure. If you're moving from this way, you reduce volume, you have increased pressure, just like we have explained. Is that okay? I think, let's see the last one. I think, is it the last one? The last one, diffusion. Let's take a look at diffusion quickly, and then we end the class. Okay. Now let's take a look at diffusion quickly. Okay. But let's just verbally explain. Diffusion is the movement of gas molecules. Okay, is the movement of gas molecule. The movement of gas molecules, not movement of water molecules. Okay, is the movement of gas molecules from region of higher concentration to region of lower concentration. For example, if you take perfume and spray perfume on your clothes, you will see if someone comes closer to you, he perceives the smell of the perfume very strongly. Or like if someone is very farther away from you. Why? Because the perfume is a gas molecule. It will diffuse from your clothes to any region around you. So the closer the person is to you, the more smelly you will perceive the perfume. The more you perceive the perfume. So that just like a dead animal also. If animal dies on the road, the closer you get to the spot, the more smelly the whole place is. So because diffusion is the movement of gas molecule. First of all, you must be able to differentiate between this and osmosis. Osmosis is the movement of water molecules, but diffusion is the movement of gas molecule. Any gas, it could be air, any gas, could be your perfume, could be any gas at all. The movement of gas molecule from region of higher concentration to region of lower concentration. Here we don't need a semi-permeable membrane. So diffusion occurs in gases when the liquid, in gases and liquid, due to random motion of the particle. And it's where particles move from the area of higher concentration to area of lower concentration. Area of higher concentration to area of lower concentration. Eventually, the concentration of particles is even as the particles are evenly spread throughout the available space. So, the concentration depends on how the particles spread out, the particle of the gas spread out. So, the area where it has the strongest smell is called the higher concentration area, and the area where you faintly can perceive the smell of the gas molecule is called the low concentration area. So, this happens, diffusion of gases increase in temperature. So if you want the rate of diffusion to happen faster, what you do here under the kinetic theory of matter, you heat the gas. The rate of diffusion of the gas molecule will increase very tremendously and spread out to other regions as fast as it can. Okay, so with this, we've come to the end of our today's class. Thank you for joining us.